Hello, everyone. Good morning, good afternoon, and good evening, depending on where you're joining in from. As you're joining in, please let us know which city you are dialing in from. We would love to understand what kind of blend of audience we have for today. So use the chat box in order to let us know where you're dialing in from, your city as well as your country. We'd definitely love to understand where our audience, our lovely audience, is dialing in from for today's session. Candidates, please help me understand where you're dialing in from. We would love to understand what kind of diverse audience we have in our for our session for today. Perfect. Perfect, guys. Do let us know where you're dialing in from. I can see a good amount of people dialing in from my home country, India. Welcome, everybody. Thank you. Please, whoever is joining in as well, please let us know where you're dialing in from. Love to understand what kind of mix of audience we have for today. Perfect. A good amount of attendees that we have. Guys, we're going to start the session exactly in 4 minutes. So do let us know where you're dialing in from. And if you have any of your friends, family members, or anybody in your network who'd also like to join, do send them a message that we are about to go live. We have our panelists ready for us today, and we would love to start this session at the earliest to help go through the entire theme, which is quite interesting for today, and also to take up the questions that you have. If you have any kind of questions, please make sure that you're putting in your questions in the Q&A section that is provided on your screen. This will really help you understand in terms of anything that you want to ask related to the theme for today's session. Along with that, if you have any questions around GWC School of Business, School of Engineering, and along with that, any kind of questions around admissions, around uh, application process, anything and everything that you have questions around, please make sure that you are adding your questions in the chat box in the Q&A section so that we can take it up during the Q&A session. Please avoid using the chats while you are putting in your questions. Don't add your questions in the chats because we might miss out on the same. So please make sure that you're adding it in the Q&A section itself. Perfect. We have a good amount of audience coming in from India. Okay, somebody from Ghana as well. Perfect. Perfect. It's lovely seeing you all here. I hope you had a wonderful day, depending on where you're dialing in from. In India, we're concluding our day for today, but it's really refreshing here to have this particular session today. An interesting topic, I must say. Thank you, everyone. We are really excited to welcome you for today's masterclass. This is brought to you by George Washington University School of Engineering and Applied Science. I am Jalda De Silva. I'll be your host for today. I represent Seed Global Education. We are dedicated towards connecting top global schools with candidates that are looking forward to exploring global degree education outside of their home country. The theme for today's session is quite interesting. It's about AI for automated mobility and traffic analysis, a journey from raw data to safer roads with AI. I am pleased to introduce our speakers for today. We have with us Professor Samer Hamadar, who is the founding director of Transportation Program at the George Washington University, professor of Civil and Environmental Engineering, with over 20 years of experience in transportation technology across the US, Europe, and Asia. He has also had research position at various leading universities worldwide and has served at multiple committees and editorial boards in transportation research. Welcome, Professor. It's lovely having you here for today.
Thank you for having me. Welcome, everyone. So,
Professor, let me quickly introduce our second speaker for today. We have with us Aaron Ward, who's the Director of Graduate Recruitment and Admissions at GW School of Engineering and Applied Science. With 15 plus years of work experience in higher education, she has led global recruitment and student-centric admission initiatives. Aaron holds a BA in Intercultural Communication and an MA in International Affairs. Thank you, Aaron. Thank you for being here with us for today. So guys, before we go across and hand it over to our speakers for today, I would love to understand what is your take and specifically what you're seeking for from today's masterclass. I would like to go across and post my first poll question for today to help better understand what exactly is our audience looking for from today's masterclass. I'm launching my first question for today. What do you think are the biggest challenges in developing AI-driven mobility system? Request you to kindly add in your answers on the poll. We're going to be live for another 1 minute. Please go across. Perfect. We have some great numbers in data accuracy and quality is trending. Perfect. Guys, attendees, make sure that you put in your answers, because this is also going to decide the course of the presentation and the kind of topic that we're going to discuss. It's an interesting topic. I understand it's quite relevant as well to a country like India. And globally as well, of course. Perfect, attendees. We're going to be live for another 30 seconds. Please make sure that you're putting in your poll response. Data accuracy and quality still is trending. Perfect. Regulation and infrastructure gap is also quite picking up, but data accuracy is still trending. So guys, put in your questions as you dial in. Please make sure that you're answering the poll question as well. We'd really love to understand what you're seeking for from today's session. Perfect. Sharing the results. Data accuracy and quality seems to be the preferred choice. Closely followed, no, actually not closely, 17% of you feel like regulation and infrastructure gap. Along with that, safety and ethics concerns is also something that a lot of you are seeking to understand more about. Perfect. Over to you, Professor.
Thank you. So, thank you all, and thank you to Seed. So I'm a professor of civil environmental engineering under the School of Engineering and Applied Sciences at the George Washington University. Today's presentation title is Advancing Automated Mobility, and mostly it's the role of AI in different aspects of mobility, starting from traffic abstraction all the way to constructing models. Now, of course, I'll be happy to further elaborate on each of the following subsections. So I will start with a brief introduction and motivation. Then I'll move to the traffic data extraction that we perform here at the George Washington University in the transportation engineering group. And then we'll talk a little bit about the models used in order to translate the traffic dynamics into models associated with human machine dynamics. And finally, I will talk about the application that we are building based on these data and the models that we are constructing here at GW in Washington, D.C. So I know that everybody is interested about artificial intelligence, and I know it's being relevant in all industries. The main thing that you should know is artificial intelligence, as you saw in the poll, is data hungry. So practically, it requires a lot of data, and practically who have the mechanism in order to extract or surf through the data will have the upper hand in constructing AI models. And from that perspective, this is where transportation play a major role. If you think about engineering in general or different applications not related to engineering, you can think about, of course, weather data, where you have a lot of data and you can look at that. Of course, you can look at language data, mostly what you have right now in ChatGPT with the natural language processing, because with that data, you can construct great models, as you see in different applications like ChatGPT applications. And from an engineering perspective, I think you would guess that transportation is a major source of data. So practically, since the start of GPS and GIS systems, all the way to the development of Google Maps and making it public, and then translating the geo data into monetized platforms that are used in social media, and more recently, the popping of all these cameras that you see on the streets and the autonomous vehicles. All of these are, again, sources of data, and transportation engineering is the main source of such data. So practically, this made us at the front end in terms of, again, leverage data for AI application in order to have, again, different prediction mechanism so that we can benefit and to improve traffic mobility and safety, or transportation mobility and safety in general. So, and you should know that in transportation, AI is not at all a future concept. You should know that AI is being used and in different applications, starting from autonomous vehicles all the way to all these traffic signal control system that you leverage, and also in order for different routing and assignment algorithm for shared ride services, for example, Uber and Lyft. So AI is being utilized. It's not a future concept anymore. It is actually an existing concept that's being leveraged by different, again, experts in the field, including at GW, with all the projects that we have and all the corresponding research. And we are translating that, of course, into different course material, educational materials. So having that in mind, before AI, if you look at transportation and traffic models, most of them were physics-based, psychophysical-based, or some of them mathematics-based, so statistics mathematics. So all of these models before, and the most relevant one were based models, practically were utilized in different scenarios, for example, freeways versus intersections. And the problem, we didn't have data in order to calibrate, validate, in order to make sure that the models that we are building, the physics model, the statistics-based model, the psychophysical-based models, all of these models require trajectories. And again, let me explain briefly. Trajectory is the XY coordinates, or if you are talking about three-dimensional space, the XYZ coordinates with every 0.1 second. So if you want good data in order to calibrate and validate all of these mobility models, you need XYZ coordinates of objects, pedestrians, cyclists, vehicles, every 0.1 second. And you tell that these data were not easy to get before. Okay. So just to give you an idea, in the 1950s, General Motors were the first, again, group that collected these data. And practically what they had a racetrack, and they had a camera, but also they have a rope connecting two cars. And the two cars were driving, and depending on the shape of the rope, they estimated the difference or the gap between car one and car two. Of course, these were 1950s, but even with the advancement up to the early 2000s, 2010s, this is not really available. So what all these detection advancements, all these communication advancements, and all of these AI advancements, mainly, like you should know right now, NVIDIA, where you have these computing powers to extract from video data these trajectories, these XYZ coordinates every 0.1 seconds. And practically, in addition to that, the existence of autonomous vehicles and the connectivity between the autonomous vehicles, so what we call connected and automated vehicles, CAVs, they are adding complexity to the traffic model, so we need even more data for that. So the primary challenge, because of all of this, is not anymore, again, related to practically collecting the data, but also to translate the data with vehicle technology into real-time dynamics and interactions, and to model the interactions not only between machines, meaning two CAVs, autonomous vehicles, but between humans and machines. For example, I'm a pedestrian. If I see let's say a way car, that's the Google autonomous vehicle car, and I'm crossing in front of it, will I have the same trust crossing in front of the vehicle if I'm crossing with a standard vehicle? So practically, this makes it a big challenge for us. And these three motivations, the models, the existence of CAVs, and the interaction between CAVs or the machine and the car and the humans, makes it a very interesting topic for us in order to move forward with our research. So what we did is we divided this research into two parts. The first part is related to traffic extraction. So how to extract traffic. And this is in it, they have AI in it. And the second part is to build the models to see how the vehicles, the pedestrians, the bicyclists, all these traffic agents moved. So you have related to traffic extraction and another part related to the model. So I'll start with the traffic extraction. So what we did is practically we went and we looked with different agencies, mostly the US Department of Transportation and the Federal Highway Administration. And practically we saw that, okay, we have already some videos associated with vehicles, pedestrians moving on the streets. We do have that. What we don't have is these videos, this kind of data associated with CAVs, meaning connected automated vehicles driving the street. So these data are kept by Tesla, for example, if you are on the autopilot mode, or by Waymo, but they are not largely shared, or they are shared in snippets. But we don't have the entire understanding of these CAVs in naturalistic, meaning in a general environment traffic. We don't have that. So we went and we said, okay, to ensure safety and the efficiency, what we want is we want data where these CAVs are driving on the streets. That's what we said. And what we ended up with a very major project called TGSIM, Third Generation Simulation Project. And practically the idea is to collect data set in order for us to get the XYZ coordinates, if you remember, these coordinates with the presence of vehicles driven by, again, humans, the human-driven vehicles, with pedestrians, with cyclists, and above all, with CAVs in between. So practically, what we did is we collected these data, and these data set, again, they are documented the operation of these CAVs and the responsiveness of the humans to these CAVs. It's both ways. And we collected these data not only on arterials. Arterials are the roads where you have traffic signals crossing. So these are the arterials. So for example, what you see in Washington, D.C. or in any major city. So practically the major roads there are the arterials. On the other hand, we collected also these data on freeways. Freeways are mainly the roadways that they have controlled access. So they don't have signals. And practically the only way you can access them is through on-ramps and off-ramps. So these two are very important. So we collected these both arterials and freeways, and we instrument vehicles, autonomous vehicles. We had our autonomous vehicles injected, and we were monitoring both these autonomous vehicles and these human-driven vehicles along with the pedestrians. So what we did is we did that not only in one location, but in two major locations. The first locations, the A, B, C locations, are in Illinois, next to Chicago. So if you practically look at the right-hand side, so what you will end up with is practically looking at a corresponding, again, a corresponding where you have the I-94 and I-294. Both of them, these are the corresponding locations. And if you look at these locations, they are very complex, but they are mostly freeways. So let me again make sure that you can see that. So practically what you end up with is you end up with a corresponding region where you have freeways, and the freeways are seen in red over here. They have complex access system. You can access them, but you have of arterials around them. Collected data on these freeways in Chicago. So we did that for, again, the A, B, and the C locations. And again, these are very congested locations. On the other hand, in Washington, D.C., it's a little bit more complex. So we did two cases. The first one is on I-395. I-395 is a region in Washington, D.C. where it's a freeway. It's one of the rare regions where you have a freeway. So practically when you enter from here, on the top side, you have the Congress. Okay, so we are in this location over here. Okay, on the map, on map D. And you can see over here, this is your corresponding Congress, that's in Washington, D.C. And in this location, you have a lot of on-ramps and off-ramps. And finally, at GW, at the Fulton campus, we also collected data in these arterials where you have a lot of people walking, a lot of pedestrians, among other features. So how we collected the data, it wasn't straightforward, of course. So what we did is we had technologies for us to collect the data. So the first part that you will see is the TGSIM Foggy Bottom. Foggy Bottom is the area where GW, George Washington University, is at. That's in Washington, D.C. So we installed 24 cameras, and practically we operated autonomous vehicles in Washington, D.C., and we collected the data for everything from cars to pedestrians to cyclists to parked vehicles for these 24 cameras. And we connected the entire block so that we have full trajectories, X, Y, Z coordinates, 0.1 seconds for everything moving in that location. And for us to extract these X, Y, Z coordinates, we use, of course, AI. We did that for detection. Then we did that for tracking, and that's another story altogether. And we, of course, reconciled the IDs. So you can see you have an ID for every vehicle. We reconciled the ID, so whenever a vehicle passes from one camera to another, practically we'll make sure that we are tracking ID pedestrians or the traffic agent in general. In addition to that, if you notice, so you can see we did that also for, again, we are staying on the top part. This part is the I-395. This is also, again, the TGSIM I-395. This is in Washington, D.C. Okay, it's very complex. And if you notice, for the cameras on the top side, both of them, they are fixed cameras. So what we had to do is we had what we call infrastructure detection. So we fix the infrastructure, and then we collect the data. And from this infrastructure, we can actually collect data again and again. So we did that in Washington, D.C. And if you know, in Washington, D.C., it's very hard to fly drones or helicopters. So that's in Washington, D.C. On the other hand, if you look at the lower side, starting from, again, the TGSIM I-90, I-94 stationary. So if you look here, these are helicopters. So what we did, we flew helicopters on top of the different freeway sections. And if you notice very closely, we are detecting every object at very high accuracy. Okay. So we have your X, Y, Z coordinates without any problem using AI technologies in order to extract that and transform them into trajectories. And we did that in different scenarios. Some of them were stationary, so practically we stay at the same location and we drive the CAVs, and then we record them again and again. The other side, if you look at the lower two sides, also by helicopter data. So practically what we did is we moved and we followed the connected autonomous vehicles. So we're following them all the time while connecting the interaction of these CAVs, connecting autonomous vehicles or autonomous vehicles, with the other traffic agents. Okay, so you can see again, you have high resolution cameras. We have, of course, stabilization technology, and we have the AI technology that we apply up in order to extract that into XYZ coordinates. And we did that in different locations, and we did that systematically with this project. So if you look here very carefully, you might see a very interesting scenario. And again, you can see here the AV. The previous cars before, of course, we have to map them and we have to recognize them. But here, this is a scenario where we are also flying helicopters that's moving. But if you look very carefully, we are following a specific vehicle. So you can see it over here, correct? So if you see it, this is your Waymo vehicle. So we rented the Waymo vehicle and we flew on top of it and we recorded its trajectories for extended periods of time. Again, we are not doing that for using drones because it can last 47 minutes, unless we have to, again, attach them to a source power. We are doing that with helicopters where we can fly for at least 2 hours at a time. Okay. So once we did that, again, we extracted all the data and we have one of the first, again, major data libraries using AI in order to understand mobility with the presence of, again, AVs. So this is that we did here at the George Washington University. And again, this is in collaboration with the US Department of Transportation. But once we have the data, that's not enough, of course. What we need to do is, of course, we leverage AI. We have a lot of sources of data. We need to translate them into models. And in order for us to do that, we need to do that again in order to model not just the AV or the CAV cars, but also the interaction between humans and these CAV cars. And we are not talking about doing that in a simulator, for example, using a gaming environment. We are doing that on the streets in naturalistic environments. And that's a major, major, major breakthrough that we are trying to do in this area. Okay, so the main thing here is we know that AI models are being used to drive some CAVs, some connected autonomous vehicles. We know that, but we don't know the characteristics of these models. Okay, so what we are doing is we are in a way translating the trajectories and not reverse engineering, but putting them against different types of models, including different AI models, to see which models fit the best. Okay, and once we are doing that, we are actually looking at the advantages of these AI models with additional or existing more traditional models. These traditional models, of course, they are of advantage. They are not, again, fully useless. But at the same time, we need to understand, is AI better or are the more traditional models better in terms of capturing either the human interactions with CAVs or the CAV movement itself? So this is a new human-machine problem. So the existing models fail to capture some complex situations, but do AI models succeed in capturing these complex situations? So now we are in a new realm and a new environment. And again, this is very interesting, but doable just because we were able to extract all these data. Okay, so you're right, data is essential. Now, in transportation, data is not the most problematic part anymore because we have data. Many different disciplines are coming to transportation to leverage this data for different applications. But the main issue right now is how to build models using AI and compare them to existing models and to see which fit the most. Okay. So from there, again, we were contacted also by the US Department of Transportation to have the next generation models for connected and automated vehicles. This is a project called NGM-CAV. And practically the objectives is not anymore to extract the data. We already did that using the TGSIM. But this project mostly is to integrate different modeling frameworks. It's not only one model, and see how advanced driving assistance systems, or what we call ADAS, and again, assistant driving systems in general, and how these two components actually can be modeled by existing models or new models, and if they can be further elaborated to what we call CAV models. Not only that, what we want to do is to build simulation. So instead of looking at the interaction between one car and one pedestrian only, we want to simulate cities. We want to simulate intersections, arterials, freeways. So we need to build the platform for that because it's not existing. So once we build the models, okay, with all the corresponding aspects from data preparation to variable selection, to doing some testing if these models make sense in terms of stability, to then test the impact of different what we call exogenous components like weather, among other features. Then we calibrate and we test the model, but above all, lately, we integrate these into different microscopic simulation platforms. We are focusing on one platform, it's called Sumo, but we are building the corresponding models within Sumo ourselves. So we didn't look at only one model. So just to give you an idea type of what we do. So for traffic models, we look at different types. Vehicles, longitudinal movement, we look at prospect theory, intelligent driver model, and AI artificial intelligence model. Diffusion models, these are another type of AI models. And of course, we look at the lane changing with the AV and the human-driven vehicles using different types of models. So in conclusion, if you look at this table, the only thing I would like you to see is how many models we have to test. And we need to compare them and see if AI work better with these models or not. And that's a major challenge in this project that we did. But again, what we were able to do is we developed these models in different environments. So if you look at the corresponding platforms, this is the platform. So this is the geometry construction of not only a small region, but a region of a city. And in each intersection, what we need to do is we need to incorporate the signal timing among features. And then we do generation using our trajectory taken from TGSIM. We customize the model and we visualize. All of this done at different locations. And just to illustrate what we were able to do. So this is, again, a very simple case using Sumo while integrating AI in a I-395 visualization platform. If you look at this, this is a freeway. This is the on-ramp. It's from the left-hand side. And practically, what we are mapping via simulation, not now collecting trajectories, via simulation, the corresponding trajectories. So we simulate the movement of every vehicle over here every 0.1 second. So if I plot the X direction here on the Y, so for example, if you look here, this is from 0 to 700. So starting 0 here, okay, at the beginning of the road, all the way to 700. I am actually looking at the XY locations, mostly at this stage, longitudinal, meaning along the corresponding length of the road. And I'm doing that every 0.1 second. Now, if you notice, whenever it slowed down, so if the vehicle starts over here and it starts slowing down, practically what will it do? It will have lower speed. So it becomes red. Okay, so the color, it indicates the speed. So if you have a red color, it means you are slowing down. So what you can see over here, you can see a region here of what we call, again, stop and go congested clusters. So you move, you stop, and then you go. You move, you stop, and then you go. This region over here is a dangerous region for what? For rear-end collisions, okay? And you should guess this is because of this bottleneck over here, because of the corresponding on-ramp. So we use simulation now to model not only AVs, not only human-driven vehicles, but to model thousands and hundreds of these every minute in order to see which region is safer, and then we can change the concentration of CAVs and see if CAVs are, again, of benefit or not. For example, we can reduce unsafe region by possibly what? By possibly injecting AVs. And we are not just doing that through modeling. These models are based on actual data that are collected. So we are closing the loop. So we did that at different scales. So we already did that at different scenarios. For example, you can see on-ramp scenarios, you can see off-ramp scenarios. We did that at intersections. Practically with the intersections, we are not doing that just with trucks. We're not doing that just with buses. We are doing that with pedestrians, and we are capturing the interaction of pedestrians with these CAVs through the data collected. So we can simulate different scenarios without any problem because that's the data that we collected. And in addition to that, what we do also is we do that at a large scale level. So we start with an intersection, for example, but if you look at the right-hand side, can you recognize where this? This is New York. This is Manhattan, downtown Manhattan. So we do that at very large scales. And we do that with millions of vehicles without any problems, using AI models and calibrating these models by data collected by AI also. Okay. So this kind of, again, technology will allow us to practically not only use models to look at the micro level, but also we can look at the macro level at a city scale. And we did that also using AI. So we have, again, looked at different scenarios. So this is using also AI, not only to look at the movement of a vehicle from a given X to another X or from a given Y to another Y, but we are looking at the movement of particles or vehicles at a city. Okay. So this is, of course, in Washington, D.C., but also we are collaborating with different agencies. So this is in Daejeon. Okay. What we did is we looked at the trajectories. We collected these trajectories because, again, as I said, transportation is a major source of data. So we can do many things using AI. So practically, we look at the map, we extract all the data from the maps, like the number of amenities, the shops, the leisure identification, the number of tourists visiting each zone. And then we map on top of that the movement of vehicles. So you can see here, these are movement of vehicles. And we use a model propagation of these vehicles along a network. So if you think about it, we are not looking at a road anymore. We are looking at a area, and we are tracking people, how they behave, and we are using AI to reconstruct trajectories in order for us to see how people move, not at the link level, not at the road level, but at the entire network level. Okay. So this will allow us to estimate what we call origin destinations. This will allow us to estimate routes choices. And again, this is using AI right now. So you can see, once we track that, you can reconstruct all these networks using AI also. So AI is being leveraged for data extraction and modeling, and for modeling being leveraged, sorry, at the link level and network level. Okay. And we are doing that where the data is collected by our research group, and the same thing is done for the modeling with the collaboration of different industry partners and the US Department of Transportation. Now, you tell me, okay, is that it? Is that what AI can do? AI can do much more. If you understand it well, if you know how to apply it, of course. So practically, what we can do with that, once we understand the models, okay, once we can simulate and calibrate existing movement patterns with CAVs, with connected automated vehicles, or without automated vehicles, we can do what we call applications. So the first application that we did is practically we are optimizing the traffic signal control, the red, yellow, green, correct? We are optimizing it using AI. So this can be only done because of the collected data. Just going back into that. Again, the good thing is in transportation in our group, we solved that problem. Okay. And we can do that also by having what we call prediction horizon. So we can tell where you are right now, and we can predict where you will be the next 5 seconds. Why is that? Because also we build the models for that. Remember, the data extraction and the sumo simulation. Both of them are done. Once you have that, what we do is we feed that into an AI controller, and then we send that to the cloud, and the corresponding cloud will allow us to simulate in real time, and then we optimize again, and then we move back. And we applied that in different applications, but one of these applications is actually in a metro station next to us, Washington, D.C. That's the Foggy Bottom metro stations. So it's over here. It's a metro station over here where you have a lot of pedestrians coming out of, and they are crossing the streets, and it's a T intersection. So vehicles can come from different locations, but they cannot go through here. This is a T intersection. And of course, the signal here is quite interesting. So what we did is we collected the data and we applied the controller in order to optimize with partial connectivities and with partial automation. And we show the corresponding again working. And again, you want to understand all of this is leveraging again AI. In this case, we are using the DQ and a deep Q network framework for us. And again, what we can do is we are changing the reward function, that is the amount of time that is needed for you to go from one area to another. And the action, of course, is to go left, right, or to cross, okay, or not to cross. And the state, it's the corresponding green, yellow, and red times. And using this framework, we can optimize without any problem, okay, using AI. So the first application is for signal control, and we did that already. The second application is actually not only now we model existing autonomous vehicles like the Waymo car, the Zoox car, but we are building our own, okay? So we are building our own autonomous vehicle, okay? So if you look on the right-hand side, so this is our own car where we can control everything from the perception aspect. So you can see over here, it's detecting everything. It's during the rain, by the way. And we have the LiDAR data. But also now, the models that we developed ourselves for simulation purposes, we are implementing them here, okay? And we are implementing them here using the detection or the what we call perception environment that we built in our autonomous vehicles. Of course, this kind of autonomous vehicles, number one, it can, of course, using cameras and LiDARs, and it detects and classifies objects, and it have a DGPS, differential GPS unit, in order to have a quiet awareness where the route is, where it's driving. And again, this will allow us to, from there, to build your corresponding, again, planner, meaning the decision to go steering or acceleration or deceleration, okay? And we are doing that. I think one of the polls was about ethical decision making or the ethics associated with AI. So we are building different types of models now. Some of them are AI based, but some of them are ethics injected AI. So we have to balance between safety and efficiency for the car and its passengers surrounding. And that's another area where now AI is being injected. Okay. So we are using prospect theory and we are injecting prospect theory. Prospect theory is a major theory in decision making that is based like theory by Tversky in order for us to evaluate risk tendencies of the people. And then we integrate on top of that AI in order to actually translate that into decisions. So practically, what we did over here is we leveraged our expertise in transportation. We leveraged our expertise in AI in order to collect data because data is essential and needed if you want AI. Okay. Even with of course, you have the GAN, generative AI, but again, even with that, data is needed at the beginning, and it's needed especially for what we call these, again, outlier scenario, okay? And then with that, we leverage the existing of videos and existing of sensors for real-time monitoring and feedback for the model calibration of these AI or non-AI based model. And then now we have one of the richest data sets with CAVs in naturalistic environments. With that, we build the models and we integrate them into simulation. And now we are building what we call a digital twin. Okay. A digital twin is you have the network, the physical network, where you have the infrastructures. We digitize it, and then these two communicate to each other in order to improve safety and improve efficiency from a traffic standpoint. So practically, this is what I had to say regarding this very interesting topic is again ability and AI. And I'd be happy to answer the questions. And then I'll leave Jelda to lead that. And of course, Aaron, if you want to elaborate further, that would be great. Thanks.
Thanks a lot, Professor, for sharing these wonderful insights with us. This was truly interesting and informative. But before we go across and go ahead with our second speaker of the day, I'd like to launch our second poll question to better understand our audience and what they're exactly looking forward to from today's session. So the question is, what factors matter the most when you're choosing a university for your specialization and master's degree? The question on your screens right now, I request our audience to please go across and answer the same. What exactly is the most exciting aspect for you, specifically when it comes to studying engineering in the US? Perfect. As the answers pour in, I would also like to take a moment and share a brief description or introduction of the host school for today. The partner school that we have for today is George Washington University School of Engineering and Applied Science. It is one of the leading universities and institutions in innovation, research, and technology. Located in Washington, D.C., GWCs offers world-class programs in engineering, computer science, and applied science, preparing students to solve global challenges through cutting-edge research and real-world impact. 30 more seconds to go, audience. Please make sure that you're putting in your choice for the question of the poll for today. A good amount of you are interested in understanding hands-on learning experience, closely followed by exposure to global industrial leadership. Wonderful. Exposure to global industry leaders is now trending, closely followed by hands-on learning opportunities. Wonderful audience. Please make sure that you're adding in your option for the poll so that our speaker for today can guide you and help you understand better in terms of what you're looking forward to. Results are on your screen right now. Exposure to global industry leaders is something that most of our audience is looking forward to, closely followed by hands-on learning opportunities. Over to you, Erin.
Yes, thank you so much. Let me just take a minute here and share my screen. Okay, tell me, is it showing correctly?
Yes, it is visible to us.
Okay, perfect. Thank you so much. Well, thanks for inviting me to speak at this session. I really appreciate it. My name's Erin Vogt. As Jelda mentioned earlier, I'm the Director of Graduate Recruitment and Admission here at GW Engineering. And I love coming to do these sessions with Seed because we always have such a thoughtful, very engaged audience with a lot of questions. Especially since a lot of those questions are for Dr. Hamdar, I'll try to move quickly through a very quick overview of our graduate programs and admissions process, in case hopefully this event has inspired you to pursue graduate education. So the first thing I want to mention that I always talk about with this kind of audience is finding the best fit program for you. So there really is no best graduate program in a certain area. It's really considering what factors are going to be the most important for you when you're looking at a program. Is it a certain type of research? Is it the cost of the program? Is it a career opportunity that you want to achieve? And really keep this in mind as we talk about graduate programs and figuring out if hopefully GW might be a good fit for you, or figuring out what school is a good fit for you. Here's some brief information about GW, about our university as a whole. We have about 25,000 students. We're unique because over 15,000 of those students are typically graduate level students, which really speaks to a high amount of resources and attention paid to studying at the graduate level. With over 2,500 faculty, you get a lot of faculty-student interaction throughout your time as a student. You'll see us mention throughout our presentation stuff like research expenditures, our membership in the American Association of Universities, the AAU. These just really speak to the high level of research that's going on at our university, which of course trickles down to benefit our students, especially our students at the graduate level. Although we do have 3 campuses, the programs that we're talking about, the on-campus engineering programs, are located on our main campus in Foggy Bottom in downtown Washington, D.C. And then here in the School of Engineering, we have 6 academic departments. We have 11 fields of study currently, more than 80 tenured and tenure-track faculty members, and then 32 million in research spending and growing every year. And I'll just point out that our fields of study and the courses that we offer, they're constantly evolving. So as we talk about topics like AI and AI's role in the different fields within engineering, you'll find our programs evolving to, of course, fit this cutting-edge material as well. A main advantage that we talk about when we talk about GW Engineering and what it's like to be a student here is our specialized departments have small to medium-sized classes. Typically, most of your classes are not going to be sitting in a lecture hall with hundreds of students, not really any of your classes. They're a smaller class size that really allows you to engage a lot with your peers and your faculty members throughout the course of your studies. Also, longstanding connections with leading organizations in the fields of engineering and computer science. You'll find a lot of faculty connections, alumni connections, peer connections with organizations that really lead to potential for career opportunities, internship opportunities, and so forth. I know one of the poll question that we just talked about, a lot of people are looking for that access to sort of leading individuals in their industry. And then this is our building, the Science and Engineering Hall. So this is the hub. This is sort of the central part of your life as an engineering student here at GW. In this building, you'll find the administrative offices like the admissions team and the other administrative offices of the school. You'll also find faculty offices, department offices, classrooms, research spaces, laboratories, study space, all sorts of things going on here. There's a lot of unique technology throughout the building. In the Civil and Environmental Engineering department, for example, there's the high bay with a strong wall and strong floor used for research. And so you'll find a lot of unique pieces of equipment or unique research opportunities, again, throughout the building. And then here's a list of our degree programs. So unless noted, they're typically offered as both MS and PhD programs. For our international students, of course, all of these programs are STEM designated, so they qualify for the STEM extension if you're interested in getting work experience after your time at GW as well. And as I mentioned, our programs continue to evolve. The courses continue to evolve as new research, new findings, new developments take place within each of these areas of study. Just a quick overview of our application requirements. Hopefully this conversation is leading you to think about what your next step is as a potential graduate student. So here are just a basic list of the requirements needed to apply. You go through our online application system. We do require English scores for most international students, just depending on where you completed your education. You can see our TOEFL and our IELTS scores on the screen. Our GRE requirement is now optional, so you don't need to take the GRE. If you have it, you're certainly welcome to provide it to us. We require 2 letters of recommendation for MS students, 3 for our PhD students, a statement of purpose, a resume, and of course your transcripts or academic records. If you're a student in India, that also means your individual semester mark sheets with all backlogs. A lot of people ask what is the most important part of the application materials, and I would say a kind of obvious answer would be your transcript or your academic records. We certainly want to see your academic success, your progress that you've made in your prior studies. The second most important thing I would say is your statement of purpose. Like, that is really our opportunity to hear from you about why you want to be a graduate student, why you chose GW specifically. What is it about our programs and our research in our areas of expertise that appeal to you? And scholarships and funding opportunities are always a big question. So I'll mention that at the MS level, we have merit-based scholarships that can range from 25 to 75% of our tuition cost. If you're awarded a scholarship, then you're just responsible for the remaining tuition costs and your living expenses. These are competitive, and they're simply based on all of the materials that you already provided with your application. So there's no additional application process for this. You'll be automatically considered based on all of the things that you provided in the application process. And then if you're a PhD student, you're interested in a PhD, most of our students who are admitted to the PhD program are also provided funding along with their admission, and that would be a full funding package that covers your tuition and a living stipend as well. And then finally, I want to mention our W. Scott Amy Career Services Center. So here at GW Engineering, we have the unique opportunity of having our own career center right within our school. So students have access to all of the career resources available across GW, but you also have access to this specialized center that is specifically for engineering and computer science students. So you have mentors, you have counselors who can work with you through the job search process, through setting up a LinkedIn profile, through developing a networking plan for yourself, through reaching out to alumni, pursuing CPT or OPT work opportunities, and so forth. So because many of our students at the School of Engineering are international students, you'll also find this office is very specialized in working with international students and the unique nuances that come with the career search for our international population. And then I just want to mention finally that if you're intrigued and you want to learn more about the experience of studying at GW Engineering, here are just a few of our student ambassadors. We have a few more on our website as well, which is mentioned here on the screen. But you're welcome to reach out and chat these students directly. So if you go to our website and you find the page that says connect with a current student, you have the ability to send chat messages and just talk to the students about what their program's like, what their living experience is like, what the community is like, all of those questions that you might want to hear from a student perspective. We really encourage you to reach out. And that's it for me. The final thing I want to mention is just that we do offer an application fee waiver for anyone who attends one of these sessions with our great partner Seed. So that application fee waiver is on the screen right now. If you note it down, it is case sensitive. So it's Seed MC 2025. Please note that, and if you do decide to apply to one of our programs, which we hope you do, this will waive the $80 application fee for you. Okay, I've gotten through everything. I'm going to stop sharing my screen, and we'll be happy to take any questions that the audience has.
Yes. Thank you, panelists, for taking us through the presentation. Thank you, Aaron, as well, for sharing the in-detail understanding in terms of the admission process, requirements, and so on. Before we go across to the questions that we have already in the Q&A section, one of the questions that prevails usually is the one that I want to ask both of you. This is specifically in relation to Professor, to you, as well as to Aaron. Whenever a student is looking forward to developing a career in AI-powered transportation solutions, what are the kind of career options that they have available in the current scenario, and how do they acquire the skills that are required in order to be employable or in order to take up projects of these kind of caliber? Aaron, to you, the question extends. How is GW helping its students, specifically in terms of helping them dig into their entrepreneurial spirit and to nurture that entrepreneurial spirit to come up with solutions that are not just AI driven, but also sustainable and applicable to the global scenario?
Well,
Okay.
those are two huge questions. Let me separate them, and I'll take a little bit, I'll defer to Dr. Hamdar about sort of the career paths and the career opportunities question. I'll just address briefly the question about how GW can nurture students who are interested in innovation and entrepreneurship. That's something that, as we've mentioned previously, is a big focus of our university, and it's something we really want to support and encourage in our students, especially our graduate student population. So you'll find resources for this across the school. One thing in the School of Engineering is our Innovation Center, which has a maker space, which allows students to go and just physically create and design and sort of invent things there with materials provided by that space, by that sort of lab space. We have things throughout the school like the R&D showcase, where we encourage students to uh, feature and be able to articulate the research that they do and what their interests and their passions are. We have things across the school, like there's a GW New Venture competition, which is really an entrepreneurship competition that encompasses not just the School of Engineering, but all the schools across GW. So that's something that's really exciting and really gives a significant amount of exposure to our students. And then finally, we have one other resource I want to mention is that students that are sort of inventing or creating or entrepreneurial in nature. We also have some legal resources and support for them, so helping with things like intellectual property issues and things like that. So we really walk students through the whole process, and like I said, it's something we really want to encourage in our student body. There's a lot of ways for graduate students to get involved. Now I'm going to defer over to Dr. Hamdar to talk more about career opportunities specific to the area of interest.
Yes. And again, the best way to explain is using examples. So I have students who are at Rivian. I have students who are at Amazon. I have students who are at Tesla. I have students who are in the financial sector who are working on AI. I have students who are actually joined public entities like Virginia Department of Transportation and Baltimore Department of Transportation. And of course, there are the consulting line of work that is more with companies like AECOM, like Leidos, among other major companies associated with transportation consulting. So practically, the range is very wide. So, and they go from tech industries to autonomous vehicle industries, all the way to, of course, consulting. And finally, you have the public sector. Now, some went to academia into the R&D also, and are doing fine. So the main thing that I would say why that variety, number one, because the students that we graduate from the master's and then the PhD, they have the enough skill set to make them a little bit different than existing what you call transportation engineers that mostly you think of when you talk about bridge design, let's say, or what you think about when you talk about pavement design or putting that traffic signal with all of these controllers that are actually outdated. So with that perspective, our skills range from, again, all the way from computer vision to programming, of course, to human factor simulation, to also build on to autonomous platforms, because practically we have a garage, an actual garage where we actually instrument cars. We have three simulators: bike simulator, car simulator, and truck simulator. We have, of course, one of the larger data platforms that you have in the name. And not only that, but the computing platforms associated with that, meaning a data center based on NVIDIA platforms. Let's put it this way. So with these skill sets, practically we are differentiated from other groups. And what we do now, in our case, we have a very competitive master program, but out of this master's program, of course, we practically, depending on the expertise or in the interest in for each one, we start building a connection accordingly. And we also link them to existing. There's another question related to, again, global entrepreneurs and leaders. So them to the associated personnel, because we are very connected, the nation's capital, but at the same time from industry perspective and academic perspective. So we pace this path, and we don't start people graduate. We start earlier. Okay, this area, these are the sets, these are possible internships ahead of time. At the same time, this will give you the power for you to continue afterwards. Now, out of these master students, who are, again, normally there are assistantship possibilities, but normally they don't work on projects as what we call research assistants. We might choose, depending on the interest of each student, a very specific number for PhD, so they can continue PhD. These are, of course, working as RAs on projects. So, but also remember, this depends on the interest of the students. Some students want after 1.5 to 2 years to go to the industry directly. We provide that pipeline. Some people know they want to continue with the research and to grow further into PhD. Also, we provide them that pipeline. Some of the master students in my group, they decided to, well, we link them to some other groups so that they can collaborate with them. So I send students to the Netherlands, I send students to Korea, and I send students to multiple universities for them to collaborate. But again, the base is in our campus. So I hope I answered your question regarding the career path and how we link them and the entrepreneurship connection.
Thanks. Thank you, Professor Hamda. We have another follow-up question, which is by Aryan. He wants to understand specifically in the developing countries, which are huge market for transportation solutions, what kind of data should we use for AI systems to better understand and manage traffic?
Now, very good question. So the most important is geo-encoded data that can be at different resolution levels, meaning I'm talking about data. And we have different ways of collecting that. Some of them using what we call probe vehicles. And actually there are different companies who are instrumented cars in general, of course, for free, but in return they get the data, but they have lower resolution. So practically they emit every 1 second, and they have GPS level accuracy of plus or minus 3 meters. So these are good in terms of routing problems or share ride service and allocation, logistic allocations. So this is good for mostly routing and traffic applications from a routing level. Now, I should note that the models there, because there's another question saying that Google already do that. Google, they are not very accurate when you talk about lane-based traffic estimation. Mostly, you don't know if you are on the right lane, and sometimes the queue is on the right lane, but practically it shows that the queue is on the entire lanes. So Google themselves, they are trying to help to improve their models. And again, because they have a good market penetration, but they have a problem with the GPS accuracy using your Google Maps application. So practically, these data are good for routing applications. If you want for phasing or control applications related to traffic signals, you need much higher resolution. So you need actually outsourced data. And normally these are not by probe vehicles, meaning by instrumented vehicles. These are by actually infrastructure sensors. So LiDARs are very good for short range, but mostly we are using mostly visual cameras for that purpose. And with that, you have the radar data in order to provide counts and speed densities, and these are good for validation purposes. So these data are essential, but again, let me repeat, these are not available, meaning you don't have a traffic system in the world that utilize thousands and hundreds of thousands of cameras, process the data in real time, get the corresponding XY coordinates, link them to a network, simulate and predict, that into AI, and optimize in real time. That's not existing. So is there in the system? There are some routing up signal timing optimization AI, but they use the vector data that you have on the streets, okay? And they are local. And again, they use many models. For max pressure is one of the models, but also you have Collide is another model. And we know about these. But these have, of course, their deficiencies, and they are not global enough. So with that perspective, geo-encoded data is the most essential one. The technology to do that in real time at large scale, it's not existing because you have a lot of computational challenges. So we know NVIDIA right now is being embedded, but it's not yet at a large scale. But also you have communication. How to communicate the data between different sections and a traffic control center. So most of the people, of course, we think that fiber optics is the best one. These fiber optics are not installed in every city. In India or in China or everywhere in the world. They are installed in some cities, but not in every city. Number two, if you want to install fiber, how about leveraging a network like a freeway network, let's say in the state of Virginia? That's huge. You don't do that using fiber networks. That's very expensive. So you need to use cellular data, possibly 4G, 5G, LTE. So these have a lot of issues in communication on how to optimize the data to be communicated in terms of bandwidth and in terms of the packet size. So the challenge is not only related to having the data, the challenge is to communicate the data and process it and then feed it in real time. And that's not an easy task, even with the most powerful GPUs.
Got it. Professor, there's another follow-up question which is on lines with what you just explained. To give you a gist of the question, what would be the next generation of innovation in predictions maze using real-time traffic data for users?
So, and I think it's also in line with one other question. So, of course, there is the mostly infrastructure-based advancement. So, how to leverage existing communication bandwidth and sensors and computation capabilities using it has optimization, but it's algorithmic optimization. That's more computer science and computer engineering in order for us to do this digital twin in an efficient and reliable manner. That's one advancement. So that's more on the infrastructure side. The other advancement is the AI models themselves. So there was another question saying about, okay, is there any psychology in the AI or is there any physics in the AI? That's what we call physics and psychology inspired AI models. You are completely correct. So practically what you add, this reward function and the corresponding AI platform, the way it actually reward a given action, it's actually constrained by the physical or the psychological aspects of the decision maker. So if you want a decision maker, for example, to learn from the experience, then you add the reward function to actually represent what we call impatience. That's one example. If you want to limit, for example, the corresponding physical qualities of the traffic itself, there's something called string stabilities. AI models are not string stable. Let me give an example. If the first vehicle stopped, the following vehicle should stop in a way, and then the third vehicle should stop so that the corresponding amplitude of the wave should attenuate. That is a string stable. Physics models that we build, we make sure they are string stable. AI model, no, it can tell you to decelerate at a range that is actually very detrimental so that the entire system will be string unstable, thus leading to real collisions. So practically you add the physics corresponding string stability so that the AI learn from it. And this is characterizing each type of environment. So for finance, different types of making, they call it psychology, it's decision-making theory, decision-making, economics-based or physics-based models. So this is the next level. Next level is how to make the AI actually learn from the physics and the psychology of the system.
Got it. Professor, our next question is around the topic that also prevailed during the poll, that is the ethical implication and social applicability of AI-driven mobility system and how it would, help in research as well as policy standpoint.
Very important. So practically, of course, there's something on the policy related to this needs to be set by the corresponding, again, legislation in every government. I'm actually on the board for Washington, D.C. in terms of licensing procedure for AI models. So the policy is inspired based on our data. The data that we are doing is, as you notice, we are modeling CAVs among other autonomous vehicles, even the basic, what we call it, adaptive cruise control systems. That's one type of autonomous vehicles. So practically, we are modeling them, and then we inject what we call ethical models, these economics-based model. So practically, there are different constructs. So for example, you have the ontological model versus utilitarian models. And with these models, we actually calibrate the parameters if you want to be more on the collaboration aspect, if you want to be on the selfish aspect. And based on both of them are ethical, by the way, from the definition of ethics. But again, depending on the weights of these, then we look at the corresponding impact at a network level or link level. And then we motivate these in order to talk about policies for the government. Okay. So based on that, we can tell them having right now, all autonomous vehicles, you can set the corresponding headway. That is 2-second headway. So most of them are 2 seconds headway. About making it larger or so that actually you can make traffic better for the entire region, or making worse for the pedestrian crossing, but better for the corresponding passengers of a robotaxi. So these things are driving the policies. Right now, there are no policy sets. Right now, we are just issuing patents in order for autonomous vehicles to operate in given environments that are less risk prone. For example, in Arizona, they can operate in low forested areas daytime. They can operate in adverse weather conditions. In DC, we are issuing the same permits. So right now we are at the permitting. Once we collect data, even in the non-risk, and we make sure that these vehicles are fine for this level, then we move with our research, for example, and we feed this through what we call the research board to the US Department of Transportation. Okay, now you need to terms of our models in order to motivate some types of ethics or some types of regulations, because ethics need to be transferred to regulations. And from the regulations, you go to what we call legislations. So, so I hope I explained the situation. So it's not there yet, even though the technology is advancing. From a legislation standpoint, we are still understanding how we are reacting to these vehicles, and react right now in one way, but in 5 years we might be much more confident. So we don't know yet. But this will be fed. Until that time, don't expect, again, large-scale deployment of autonomous vehicles with different operators.
Got it. Thank you, Professor. Now we'll move our direction to a few academic and admission-related questions, since we are a little pressed on time. And if a lot of students have asked a question around application and admission, so I'm just going to club it down and ask one specific question to you. What, according to you, should be a checklist that the student should follow, specifically when it comes to applications and admissions related process, in order to make sure that they are into the counting of being admitted to your institution?
Sure. I would say the best advice I have would be to jump on our website or any other universities that you're considering applying for, look at the application requirement, look at the deadlines for the application, which are so important, and then just kind of map out a plan of what needs to be done when. So what we see a lot of cases are students trying to apply at the last minute. They're trying to apply like on the deadline day, and then they realize, oh wait, I don't have my individual semester mark sheets available, or I don't have everything that I need to complete the application. So I always tell students to kind of look now. This is the perfect time of year to look at all the requirements for GW for our MS programs. Our application deadline is January 15th. So ideally, you will start working on the application in November, December, and you'll make sure that you have all the requirements ready. I think just paying also close attention to the detail of what's required. Like I mentioned, for us, the individual semester mark sheets are required. Maybe other universities don't have that requirement, but just making sure that you provide the right materials, it gets you a decision faster, because then we don't have to go back and forth with you about missing documentation. That's my best advice.
Yeah, thank you. Another very common question is how does an international student look at living and accommodation options while at campus? Do you have any kind of recommendations? How do you recommend to go about with finding the right place for living, specifically when they're enrolled in the program?
Yeah, great question. So with our campus being like a downtown urban city campus, we actually don't have housing available for graduate students like in the form of dormitories, but we do provide resources to students to help them find housing in our area. So we have a website specifically for off-campus housing opportunities, and that's where we direct our graduate students to find a lot of local apartment buildings and opportunities that they might want to pursue. There's also a roommate board, a messaging board where students can connect with other students who are looking for housing as well. So we recommend that. And then the last thing I'll suggest is typically for each incoming class here at the School of Engineering, we open it's called a community. It's through something called Unibuddy, a Unibuddy community. And that's like a virtual platform where students can get into the platform and talk to each other before they arrive on campus. And what we find is each semester, a lot of the discussion in that platform is about housing. So students are saying, oh, I have an extra room, or have you found a place to live yet, or that kind of thing. And so that's where a lot of our students actually connect with each other and start to connect privately and discuss maybe being roommates or learning where their peers are going to be living as well. So that's an opportunity that again happens for admitted students, but before you arrive on campus in the months leading up to the beginning of the semester. So there's a lot of resources provided to help students connect with housing opportunities.
Got it. Our next question is from Christine, which is also an interesting question. What kind of interdisciplinary collaboration opportunities do exist at GW Engineering? And specifically when it comes to engineering as well as sciences or engineering and collaboration with business schools, etc.
So I can answer this broadly, and then I'll defer if Dr. Hamdar has something to add about sort of the faculty perspective. But in general, interdisciplinary studies is a big focus of GW, and it's something that our university really tries to emphasize, whether it's across school or just across disciplines like within the School of Engineering. I personally know of a lot of experiences with faculty where, you know, a faculty is technically a member of the electrical engineering department, but they do research with this other faculty member who's in the computer science department or something like that. That's quite common at our school. You see the same thing at the student level. Many of our programs like allow some electives for students to take, and they're allowed to take those in other engineering disciplines. So maybe if you're a civil student, but you want to take a computer science elective or something like that, that's typically allowed. And our programs are designed because we really want to encourage our students to do that. Likewise, I've seen students engaged in research projects that span multiple departments. So maybe they're a data analytics student, for example, and they're doing some interesting research in the topic of autonomous vehicles, and maybe they want to, you know, collaborate with a few professors that have really good backgrounds in data sets in that area. And so, you know, you'll see a lot of that type of collaboration across the school. So that's really about sort of the spirit of collaboration. I don't know if Dr. Hamdar has any more specifics that he would want to provide. But...
Thank you. And in the meantime, I'm trying to answer as much as possible questions by writing, but whenever I will continue until I don't have more time. But the main thing is, okay, my research group, they have computer scientists, we have mechanical engineers, we have electrical engineers, and we have civil environmental engineers. So my colleague has mathematics again. So this is just to let you know that in our group, transportation engineering, the corresponding background of the students is very interdisciplinary. And most of these students, in a thesis perspective for the master's or the PhD, for those who are chosen to continue PhD as RAs, but always we incorporate students that faculty in their committees from other departments, and we co-advise from a research perspective. So practically, I have right now, I told you, so mechanical engineering, we have one, the faculty member with me that's working with me is in control, mostly working on robotics. That's a student working on AVs. A second one who is working mostly on, again, percolation theory, this kind of traffic dissipating, are mechanical engineering faculty members. Sworn and urban, on sworn mobility, meaning mobility in the air. And last but not least, my student working on the edge computing devices that link to the camera so that we can optimize the performance of the traffic, definitely computer science. So practically the way we work, again, because our faculty, they have very good interaction with the students, almost at, again, individual level in terms of advising. So we choose always our colleagues from other departments in order to co-advise. and to gain their expertise, because our research topic in our group, at least in transportation, is very multidisciplinary. So that's just some examples. And again, we'll continue this way, and I think that's a recipe for success. So even if you are, for example, a computer engineer, or you are a mechanical engineer working on robotics who is focused on, let's say, computer vision. Some of them, they are continuing masters in transportation engineering, and then some of them are continuing PhD in transport engineering. And even if you look at faculty members, by the way, in transportation engineering, not all of them are civil engineers as a undergrad education. Many of them are physicists, mathematicians, computer scientists recently, not before, because of what's going on with the industry and autonomous vehicles, like what happened in different, again. But so the skills that we need at this level is actually based on your analytical background, depending on your area of expertise. But then we build it with the master level courses, programming, AI, computer vision, human factors, autonomous vehicles, etc. And then traffic engineering, just to know the concepts, what's safety, because some of the questions I'm trying to answer, it means that they need to understand more about traffic, how we quantify traffic, how we model traffic. And then there you go to the PhD. So practically you take these tools, okay, and you go and have these kind of, again, breakthrough that are non-existing anyway. For the master levels, once you finish the master level, because you have these tools, these courses, you are ready even with these courses, with your background, with the additional tools, because all of our tools are applied, as I told you. You can go direct to the industry with this added level.
Thank you, Professor. My final question for today's session is to Aaron. Aaron, there's a lot of speculations around study in the US currently, with a lot of new policies and the courts doing headlines on a daily basis. Do you have any advice for the international students that are currently considering intake 2025-26? What are the key aspects that they should be looking out for? You definitely mentioned how they can reach out to campus ambassadors and better understand the campus life. But do you have any kind of advice that you wish to share with these individuals?
Yeah, I think obviously that in the US, we're going through a lot of changes right now, whether it's, politically, culturally, just trying to figure out. And we understand that for international students, there may be a lot of change or ambiguity or headlines that maybe cause concern. I really encourage students to look closer at the individual universities that they're interested in attending, to really kind of try to get a sense of the community, the culture at that university. Universities generally tend to be extremely open to international students and have a very thriving international community, a diverse community, and are very welcoming on a whole. I think the city of Washington, D.C. as well. It's a very international city. It's the location of our embassies, of a lot of international organizations and so forth. So you'll also find sort of thriving international communities across our city as well. The other piece of advice I have is to keep in mind that when you're considering applying for a graduate program, especially even just at the MS level, our MS programs are 2 years. If you're considering applying now, then you'd be starting next year. So you're talking about graduating at the earliest, maybe 2.5 to 3 years from now from your program. And a lot changes in 2.5 to 3 years in terms of whether it's, what's going on politically, whether it's the economy. It's really hard to predict what situation we'll be in at that time. So I just really encourage students to think about what their individual goals are and to be driven by sort of achieving those individual goals. And the system and the universities will evolve in that time, but we're still here to support international students. And a lot of our graduate students, especially in the engineering school, are international, and there's just a lot of supports in place for them to help them figure out what their path is, regardless of whatever constraints are going on around them. So.
Thank you, Aaron, for this insightful session and walking us through how students can take the next step with GWCs. A big thank you to Professor Hamdar for sharing such valuable perspective on how AI is transforming mobility and transportation. I'd like to thank all our attendees as well who have joined us and have actively participated in this session for today. If you are looking forward to learning more information about George Washington University School of Engineering and Applied Science, do reach out to the SEED team. We are here to help you out with any and everything that you require, specifically in terms of your application and admission journey. Anybody who's looking forward to scholarship options, etc., can also check out our scholarship page. We have in detail information around scholarships that are provided by individual institutions that you can go check out and get more information about. For any further information, you can always write down to SEED Global Education, info@seedglobaleducation.com, or you can reach out to us directly on our social media platforms. We will definitely be able to help you out on that. On behalf of SEED Global Education and GWCs, I once again thank you all for joining this session. Thank you, speakers, and have a wonderful, wonderful day ahead.
Thank you all.
If you're winding up your day for today, have a great evening.
Thank you. I think I answered all questions. Anything else, let me know afterwards. Thanks.
Perfect. If you have any questions that you would want us to, direct to the speakers for today, do reach out to us, and we'll make sure that we move your questions to the speakers for today. Have a wonderful day, everybody.
You too. Bye-bye.